two types of dynamic range, two types of log compression that happens within the system, correct? This is basically focusing on what happens in the system that we don't have any control over. Not the compression button that we can change, right? So that's adjusting our shades of gray. But remember, the first function of compression is to adjust the signals, right? So the signals are within the range of the actual system itself, right? Right, guys? Okay, so think of dynamic range as the number of available choices. Okay, so if I have a low dynamic range, a real black and white, narrow dynamic range, a real black and white image, my number of available choices is less. I don't have as many available choices, right? I have black, gray, white. Okay, when I have a high dynamic range or a wide dynamic range, I'm going to have a lot more number of available choices. I'm going to have black, all of those shades of gray, in between there to white. Okay? I'm going to have a lot more choices to pick from. Okay? I'm going to have a lot more visualization on the structures. Okay? So, again, dynamic range, it's like compression, right? It's compression. It's measured in units of decibels. Okay? Again, this chapter is focused on what's happening in the first part of dynamic range, the first part of compression. What is the system doing? Okay, that keeps the dynamic range within the parameters of the system, right? Because that's the first part of compression. Okay, so that's what this chapter is focusing on. This is the first part. What happens during the first part? Now what happens during the second part when we adjust it? Okay. So, dynamic range, for example, it's a scale that accurately weighs objects between 30 to 300 pounds. This is so funny to me. Okay? But that's our example. So just imagine a scale, it can weigh things accurately between 30 to 300 pounds. Meaning that anything under 300 pounds, anything over 300 pounds, that's the maximum, saturated. Anything below that, it hasn't reached its threshold. Okay. So, again, like I just said, signals below 30 pounds, they're too weak to cause a reaction for this scale. Okay? Weak signals are below the system threshold. We're good there? They don't weigh enough to cause a reaction by the scale. That's what the threshold means. Okay? It hasn't reached the minimum magnitude to be recognized on this scale. Okay? It may come up as an error if you're too light. Same thing, it may come in as an error if you're over 300 pounds. Okay? So, signals that are above 300 pounds are too strong, are too much. Okay? These signals saturate the system. Okay? These signals saturate the system. Therefore, the scale's range of accuracy measurement is from 30 to 300 pounds. Correct? I mean, I'm only going to get accurate measures between those numbers. We're all safe in here. We can get on this scale. Accurate. Okay? So this system is between 30 and 300 pounds. That's our dynamic range. Essentially, guys, grapes, they're too light. You know, we need a different scale for that, right? Or like the book says, a car is too heavy. It's not going to accurately measure these things. Okay? But this scale can accurately measure an average human, average person. Okay? So we can report that 30 to 300 range as a ratio. But remember, the ratio is a comparison. It's a relative figure, right? We learned this talking in chapter 6, interaction of sound and media. Okay? So we can report a 300 or 30 to 300 difference as a 10-to-1 ratio. Okay? The largest signal is 10 times greater than the smallest. 30 times 10 equals 300. 30 times 10 equals 300. Okay? 10-to-1 is not in the appropriate form, right? Because we know that dynamic range have units of decibels. What is this decibel?
Ratio.
I know, but what is this decibel? If I had to report this in decibels, this ratio, if I had to report this ratio in decibels, what is it?
10-1.
10 decibels, right? 10 decibels. 10 decibels. Remember, whatever this number is, that's how many zeros you're gonna put behind it, right? It's just one. That means you're gonna have 1 0. That's 10. If I had 20 decibels, that's 2 zeros. That's 100, right? Okay. Same thing. If I had 12 zeros, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's a trillion right there. That's a trillion to 1 ratio with 12 zeros. If this was 120 to 1 ratio, okay, I'm gonna take the number. That's how 12 is the whole number. Know how many zeros I have to put behind it. Remember, decibels are based on factors of 10, correct? Based on factors of 10. So if I have 120 to 1 ratio, then that's gonna be 12 zeros, with 12 zeros equivalent to a trillion. Okay? So in essence, if I had that on here, I could say that the highest signal is a trillion times stronger than the lowest signal. Okay? And I use that number for a reason. We're good there? So whatever the whole number is in front of the zero, that's how many zeros you put on, that's how many zeros you apply to your decibel notation. Okay? Same thing. If it's 6 zeros, 60 decibels, that's 1,000,000 times. Okay? We good there, guys? That should be refreshing. 6 zeros, yeah. 6 zeros. You're gonna report 6 zeros as 60 decibels. Okay? We're saying that our largest signal is 1,000,000 times bigger than our smallest signal. Okay. Remember, dynamic range, decibels. So let's talk about the dynamic range of the system components, meaning the parts that make up our ultrasound system, from the transducer all the way to the storage. Okay, we already know that because we talked about that in chapter 14, correct? All right, so the individual components of the ultrasound system all have different dynamic ranges. Remember, like I said, when I took this image from the last chapter on my phone, it looked great. But when I processed that information and sent it over to through email, it probably got compressed on the way there. Okay, it probably lost some of the dynamic range. It lost some of the quality that I originally had. Okay, and I already lost quality from me taking the picture from the book. Right, the book is the perfect picture. I take a picture of that, I lost quality. Right, think about it. When you take a picture, you taking your selfie. That don't always, unless you got a filter on, that don't always look exactly how you want it to look. You're like, man, that ain't me. That ain't how I'm looking right now. You know what I mean? In person, right? So every time information is being processed, it loses a little quality. Okay? Same thing. The ultrasound system does the same thing. The individual components have different dynamic ranges. So when we talk about the transducer, it has a higher dynamic range than, say, when we archive or save that information. Okay? So the transducer operates at around 120 decibels. That's its dynamic range. Right? 1 trillion times, right? It's 1 trillion to 1 ratio. Okay? We have that's our number of available choices when we're talking about the transducer dynamic range. I'm just trying to get you guys to notice that information, as it travels through the ultrasound system, it loses information. Okay? We're losing the number of available choices every time the information is being processed. Okay, so we talk about our transducer, 120 decibels. Our receiver, okay, our 5-function receiver, 100 to 120 decibels. Okay, our scan converter, that's the part before it goes to the display. That's basically taking the analog information we're getting from the receiver, converting it to digital information. Okay, that's what the scan converter does. We're going to cover that chapter 15. Okay, displays it in its processing. Okay, and then it goes to the display, operating at about 20 to 30 decibels. What is that? 100 to 1,000. Okay, that's the range. Okay, that's 100 to 1,000. All right, and archiving is about 10 to 30 decibels. Okay, like for example, y'all biggest, the biggest thing I would say is, say for instance, when you're in MFM, you guys have been showing me images. I'm like, man, what's up with this gain, right? I've been complaining. Every time you showing me an image from MFM, whoever showed me images, I'm like, what's up with the gain? You like, oh man, but on the screen it looks perfect. That's true. That's true. It has everything to do with image processing, right? It has everything to do with your dynamic range. We're losing those shades of gray, right? When you show me images, I'm like, you like, man, the game was perfect when I took the picture. When I took the picture, right, at the display. But when you save that image or you printed it out, we lost some signal between that function. Okay. So that's my explanation of how that's going into effect and how it affects you guys every day when using that film. Okay. Digital, it still affects it. You're losing quality every time, but just not as much as when you're doing something analog, like printing something out. And printing is considered an analog feature. Okay, it's not a digital feature. So, as a general rule, I stated this a couple of times, the dynamic range of information decreases the more it is processed. Okay? The dynamic range of information decreases the more it is processed. Meaning we're losing the number of available choices we have every time information is being processed, from the transducer, to the receiver, to the scan converter, to the display, to the image, up to the storage, okay, to the archiving. The components earliest in the imaging chain, such as the transducer, process with the widest dynamic range. They have the widest number of available choices. Okay? The components further along the imaging chain, the display and the storage, they process data with the narrower dynamic range. Makes sense, right? Again, we're losing information every time an image is processed. So yeah, with the transducer, you're gonna, it's operating, man, it may have a million shades of gray. By the time we get to the storage, it may have 10. It may have 10. Because every time we process information, it's losing it. It's losing information every time it's being processed. Okay. So here's kind of like how it works. So our threshold, meaning that's our minimum, right? Is going to be less than the input signal, which is less than the saturation, right? Saturation means we're over the dynamic range. We're above the scale. Okay. The minimum threshold meaning that we've yet to reach that scale. Okay. So again, we have our transducer right there. Information we know it comes back to the beamformer, right? First, that beamformer has a switch, right, that protects the system components, protects the receiver specifically from those high voltages from when the image is being when the beam is being transmitted. Okay, so after it goes beam transducer, beamformer, back to the beamformer right there, then to the receiver, then it has the scan converter. Again, the scan converter, like I said, we're going to elaborate on that next chapter. Okay, we're going to elaborate on that next chapter. On the chapter 15. Okay, and then from the scan converter, then it goes to the monitor and the storage and archiving. Okay, but as you can see, regardless, image information is being lost. The more we process the information is being lost. Okay? There may be problems when the dynamic range of one component is narrower than that of the other. You see how information can get messed up if the dynamic ranges are different, right? That means inaccuracies can happen. Okay? The dynamic range of the system receiver may be 100 decibels, but the scan converter is only 60. Okay? So we're losing a lot of information, right? But most importantly, if nothing is done, inaccuracies can occur. Okay, things can be projected in the wrong shade of gray, basically. All right. So the process of compression eliminates these potential errors, right? Because that's what compression does. Okay, that's what compression does. The process of compression eliminates the errors that can occur because these system components have different dynamic ranges. Okay. The human eye is narrower than that of the system display, and also the image must be compressed for that as well. We know that's the second portion of compression, right? That's the second portion of compression, is that the image gets compressed again, so we're able to see that range of the shades of gray. Okay. Compression technique reduces the dynamic range of the signal without introducing errors. Okay, of course, yeah, we don't like errors, of course. So again, this is my summary of it. The largest signal remains the largest, our brightest white is still gonna be our brightest white on the image, okay? The smallest signal remains the smallest. Our darkest black is still gonna be the darkest black, okay? Only thing that changes the range of signals within between black and white. That's what's changing when you change your dynamic range, when you change your log compression, when you change your grayscale mapping. Okay. So, an alternate description to dynamic range is the number of choices. Remember, I've been saying that the whole time. It's changing our number of choices. Okay. The dynamic range of a display can be reported as the number of possible gray shades. So, with a narrow dynamic range, we're going to have fewer shades of gray. Correct? Fewer shades of gray. Okay. We're going to have a bistable image, which bistable means a black and white image. Okay. It's going to be black, gray, white. Okay, with a narrow range. You don't have many choices. Okay? And it's going to be, that's considered high contrast. High contrast meaning it's a black and white image. Okay? When we have a wide dynamic range, we have many shades of gray. It creates a grayscale image, an image with multiple shades of gray in it. Okay? And that's going to be considered low contrast. Alright, so here it is on display right here. And again, I do have a video of me changing the dynamic range at my other job where you can see I don't have a real image. You can just look in the near field and see that the grayscales are changing. Okay, so we have a system operating at 90 decibels, right? That's our high dynamic range compared to something that's 30. Remember, 30 meaning it's narrower. It's going to have a more black and white image. You have this image real black and white. Our white is still the whitest. Okay. Wherever the brightest signal is, it's still gonna be the brightest, okay? In comparison to this image right here, which is showing more shades of gray. Okay. That's it, guys. Can I hit the lights, bro? That's it, guys. Just real quick on dynamic range. It's just telling us. My quick summary of dynamic range is that all the system components have different dynamic ranges. Compression fixes that so we don't introduce errors. Okay. Guys, test on Wednesday. Any questions? Okay, and yeah, guys, matter of fact, I got questions. Let's do these questions in the back of that chapter and that's the reason I wanted to cover this chapter right now, because it's really simple. When we're talking about dynamic range and how it's going to change, it's really simple when it comes to this style of questions in the back of the book. What page is that? It should be page
261.
To what?
261.
67.
Yeah. So it's just the application of addition and subtraction, right? That's all it is. And these kind of questions are pretty simple to figure out. You just have to, know how to work them. I wouldn't even say they're difficult to comprehend. Okay? So I'm going to do question number 1 and number 3 because those are the ones that are pretty simple. Okay? So, number 1, guys, I'm on page 267, number 1. Okay? It's pretty straightforward when we're dealing with decimals. Okay? So, number 1 says, an uncompressed signal within the receiver of an ultrasound system has a dynamic range of 110 decibels. The signal undergoes 40 decibels of compression. What is the dynamic range of the compressed signal? Simple, guys. 110 minus 40. Our new compressed signal is going to be 70 decibels. Okay? I may write that in a number format, right? With 7 zeros. That may be, what's that? 10 million? 7 zeros is 10 million, right? But it means the same thing. Okay? But it's just that simple when we're talking about trying to figure out, hey, if you already know that 110 minus 40 is 70 decibels, and I give you the number 10 million, you're just gonna count the zeros, correct?
Mm-hmm.
I'm not saying I am. I'm not saying I'm not. I don't know. I haven't made these questions for this chapter yet. Okay. So let's do number 3, because it's basically using the same numbers. Okay. After compression, a signal within the ultrasound system dynamic range has a dynamic range of 70 decibels, meaning we already know what it is after compression. Okay? the original signal was compressed by 40 decibels. What is the dynamic range of the original uncompressed signal? Okay. In this case, you're just gonna add those numbers. 70 plus 40 is gonna equal 110 decibels. Okay. Real simple to understand, right, guys? Okay. And that's it right there. I know this class ends at what 9:30, right? Or 9:40. I'm sorry, 8:40. 8:40. But if you guys don't have any questions for me, then I'll just give you the rest of this time. We're good?
Yep.
No questions about chapter 14 either? Yes, ma'am. I got a question right here, Mr. Seal. One second. I got a question right here, Mr. Seal.
The one that has to be in orders.
The receiver?
Yeah, the receiver. What does it mean in order? Do you have to adjust each one?
No, you don't have to adjust.